Okay, so this video is going to look at transformations of random variables as well as combinations of random variables. We've done transformation before, and your rules are basically the same. So let me give you a couple reminders of what we did before. So before we transformed data, we added and or subtracted a constant from the data set. Remember, when we subtract or add a constant from the data set, that's going to add or subtract the constant from the measures of center. Like, for instance, if I had a mean value and I add or subtract a constant to every data value within that data set, it will then change the mean by that same constant. So remember, our measures of center are mean, median, quartiles, and percentiles. Remember, though, adding or subtracting a constant will not change the shape or spread. Okay, so it does not change the shape or spread. Okay, remember, our spread essentially is our range. Okay, so our spread is our range, and remember that's a single-digit value. Our IQR, as well as standard deviation. None of these things will change if we add or subtract a constant. Now, if we multiply or divide every value in our data set by a constant, that will also do the same to our measures of center. So again, our mean, median, quartiles, percentiles will all change, either multiplied or divided by that constant. It will also change our spread. Okay, so our measures of spread, like range, IQR, standard deviation, those will all change by that multiplication or that division. However, the shape does not change. Remember, the shape never ever changes. Okay. When we're talking about variance, which is going to be important in this particular set of things that we're going to be doing. So when we're talking about variance here, you cannot just multiply the variance. You will multiply the variance by the constant squared. Okay, so keep that in mind. Again, when we're referring to variance here, and if I've multiplied or divided by not dealing with the addition or subtraction here, but if I multiply or divide my data set by a constant, when I'm figuring out the variance, which is important for figuring out standard deviation, okay, I'm going to multiply by that constant squared. And you'll see that in these examples that we're going to do. Okay, so let's look at what happens with this example here. You're going to see this example throughout this video. We're going to keep coming back to this example, as well as the example with the cars on the Friday morning. So we've got Pete, who charges $150 per passenger to do his tours. Capital C is the total amount of money that Pete collects on a randomly selected trip. Because the amount of money Pete collects is just 150 times the number of passengers, we can write that C equals 150x. So you can see that right here. From the probability distribution of x, we can see that the chance of having two people, so x equals 2, on the trip is 0.15. In that case, C equals 150 times 2. So the amount of money he would collect times the passenger equals $300. So one possible value of C is $300, and its corresponding probability is 0.15, because 0.15 is the same probability as if he had two people on the trip. If X equaled 3 people on the trip, then C, the amount of money he collected, would be $450, and the corresponding probability would be 0.25, because again, that's the corresponding probability for having 3 people on the trip. So you can make your probability distribution based on that. You can multiply by your constant to figure out your probability distribution. Okay, over here we've got a histogram of this probability distribution here. You'll notice the shape is basically the same. Okay, everything else does change though. We're multiplying by a constant. Remember, we're going to multiply or divide to get our measures of center and location. It multiplies or divides our measures of spread as well. Okay, so the mean of C is right here. Okay, the formula is the same as it was before. All the values of C times all of their particular probabilities. So using the probabilities that we calculated from this table here, okay, we can see that the mean is 562.5, which means on average, Pete's going to collect a total of $562.50 from each trip. Okay, when we do the variance for this problem, okay, you cannot go straight to standard deviation. You're going to have to do variance first. So when we do the variance for this problem, it's the same formula. Again, each value of C minus the mean squared times the probability of that happening. Okay, so I have, you can see your first value put in there, 300 minus the mean of 562.5 squared times the probability of that happening, continuing all the way through. And then that is going to allow me to get my standard deviation, because remember that my standard deviation of C is equal to the square root of the variance of C. And so my new standard deviation here is $163.46. So now you can see as we put up this histogram here, which is the histogram showing of the distribution, the probability of him having those numbers of passengers, and we compare it to this histogram over here, which is our probability of the money collected, you'll see the shape is the same. Okay, my measures of center have shifted by 150, okay, because I was multiplying everything by 150. Okay, and my measures of spread have shifted as well. The center in my original one here was 3.75, where the mean, okay, the mean of the collected is 562.5. Oh, I ran out of room there. Okay, which is 150 times 3.75. Okay, the spread here in the original one is 1.0897 is my standard deviation of X. Okay, whereas my standard deviation of money collected is 163.46, which is 150 times my standard deviation of the first probability distribution. Okay, so now let's take a look at what happens if we add or subtract a constant. Okay, so remember when we added or subtracted a constant before, it changed our measurements of center and location, but it did not change the shape or the measures of spread. The same happens here for random variables as well. It will change the measure of center and location by the value of the constant that we added or subtracted, but it does not change the shape or the measures of spread. So let's look at an example again with Pete's tours. So it says here that it costs Pete $100 to buy permits, gas, and a ferry pass for each half-day trip. So the amount of profit is going to be V that Pete makes from the trip is the total amount of money collected that he collects from his passengers minus $100. So V is equal to C minus 100. If Pete has only 2 passengers on the trip and X equals 2 then C equals 2 times 150 or the $300 and V equals $200, 300 minus the 100. From the probability distribution of C, the chance that this happens is 0.15, so we can use that as our probability that V equals 200. Again, like let's, if we said, for instance, that Pete had 3 passengers, C is equal to 450, V is equal to 350. Again, using our probability distributions from before, okay, the likelihood of him having 3 passengers is the same as the probability that he is going to make a profit of $350, and so that probability is 0.25. Okay, over here, we've got our histogram of this distribution. You'll notice again that the shape is basically the same, okay, and the spread is the same, yet our mean has shifted. Our mean and location has shifted a little bit. So in this case, the mean of V, we would calculate it the exact same way we calculate any of the others. Every value of V times the probability of that happening. You can go through, you can calculate all of them, okay, and you will see that the mean here is 462.5. Well, if you think back to the mean of C, it was $562.50. So we have subtracted $100 from the mean of what was collected. We've subtracted our constant from that. Okay. Our variance here, you'll notice we go straight to variance. So our variance here is calculated the same way again. Every data point minus the mean squared times the probability that that data point will happen. Our variance here is $26,718.75. When I take the square root of that and get the standard deviation, I get $163.46. And if you remember from our previous example of the money that was collected, our standard deviation was the same. It was $163.46. Okay, so let's look at another example here of this. So we've got the large auto dealership keeping track of sales made during each hour of the day. Let X equal the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability of distribution of X is as follows. So we're going to follow this one and the Pete's Jeep tours throughout this video here. So my random variable X has a mean of 1.1 and a standard deviation of 0.943. Okay, and so part one here is suppose the dealership's manager receives a $500 bonus from the company for each car sold. Y equals the bonus received from car sales during the first hour on a randomly selected Friday. Find the mean and standard deviation of Y. Okay, well, if Y equals the bonus that's received, okay, then basically Y equals 500 times X. Okay, so if I want to figure out what my mean of Y is, I can take 500 times the mean of X, which is going to give me 500 times 1.1, which will in turn give me $550. So that would be the average bonus that the manager would receive in the first hour of business on a randomly selected Friday out of many, many Fridays. Okay, to find the standard deviation of Y here, okay, I can do the same thing, right? My standard deviation of Y is going to be equal to 500 times the standard deviation of X. So, because remember, I always have to show my work. 500 times 0.943, which is going to give me $471.50, meaning that he will typically vary from that $550 by $471.50. So part two here says to encourage customers to buy cars on Friday mornings, the manager spends $75 to provide coffee and donuts. The manager's net profit, T, on a randomly selected Friday is the bonus earned minus the $75. Find the mean and standard deviation of T. So when I'm looking for T here, T, okay, is the manager's net profit. So I need to keep in mind that T is going to be 500 times the amount of cars sold minus that $75 that he spends. Okay, we can also write this as Y, because 500 times X was Y, right? Minus that $75. So if I want to find the mean of T, okay, I can just subtract the Y, the mean of Y, right? Which is the mean of Y minus $75, which then would be 550 minus $75, which means he has a average net gain of $475. If I want the standard deviation of t, right, so my standard deviation of t, this is going to be the standard deviation of y minus 75, which is going to give us $471.50. So now let's look at what happens if we transform with both the addition or subtraction as well as the multiplication or division. This is what we call a linear transformation. That's an F. And so the linear transformation is doing both transformations, again, adding or subtracting by a constant and multiplying or dividing by a constant. We write that out as y equals a plus bx, right, where both a and b are constants. Okay, this applies to both discrete as well as continuous variables. And what happens here when we do this is our shape stays the same. Noticing a theme here, shape always stays the same. So shape stays the same as long as b is greater than 0. What happens to my center is multiplied or divided by the constant first, and then you do the addition or subtraction. Okay, but you have to make sure you're going to do it in that same order. For example, my mean of y would equal a plus b times the mean of x. So I do my multiplication or division first, and then I do the addition or the subtraction. My spread is multiplied, because remember that multiplication or division, so my spread is multiplied or divided by the constant, because that impacts the spread, but it is not subtracted, okay, or added. You do not add or subtract the constant. So our standard deviation of y here would equal multiplying by the absolute value, in case it was a negative, okay, times the standard deviation of x. But it is not, you do not add or subtract anything to the spread. So this example here is called the baby in the bathwater. So one brand of bathtub comes to the dial to set the water temperature. When the baby safe setting is selected and the tub is filled, the temperature of x of the water follows a normal distribution, so that's important to us. Okay, it follows a normal distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. Set the random variable y to be the water temperature in degrees Fahrenheit. Remember, this is our formula here for calculating temperature from Celsius to Fahrenheit. When the dial is set on baby safe, find the mean and standard deviation of y. So we're working with a normal problem. Remember, we've got our 3-step process, so we need to state our interest, our parameters, perform our calculations, and then we're going to need to actually write down what it says, okay, in context, interpret it, actually answer the question. Okay, so for step 1, okay, we are trying to find the probability that it is safe, right? So it is meaning that that y is between 90 degrees and 100 degrees Fahrenheit. Well, the problem, we're not in Fahrenheit yet. So we need to take our Celsius data and we need to convert that. If we know that y, right, y is our temperature in Fahrenheit, okay, so I can take that my mean of y is going to be my mean of y is going to be my mean of x times 9/5 plus 32, right? Because that's my constant. So it's going to be my constant 9/5 times my mean of x, right, plus my constant. And when I solve for that, that is going to give me 93.2 degrees Fahrenheit. Okay, and then my standard deviation for y is going to be the absolute value of the constant that I'm multiplying it by times my standard deviation of x, which is 2 degrees, right? So times 2, which is my standard deviation of x, which is going to give me 3.6 degrees Fahrenheit. Remember, I do not add or subtract the constant to a measure of spread. So when I'm defining my parameters and stating my areas of interest, this is the kind of thing that I'm going to write. Okay, that I have y is a normally distributed with a mean of 93.2 and a standard deviation of 3.6. What you're looking for, and you can even draw your picture, right? My normal distribution, 93.2. I'm looking at 100 and 90, and this is a normal curve with a mean of 93.2 and a standard deviation of 3.6. Okay, and I'm looking for this area under the curve there. So step 2 is going to be to actually perform my calculations and actually solve. And there's 2 ways you can do this, right? You can do this with z-scores or you can do this with your calculator. Okay, so if I'm doing this with my calculator and I'm showing my work, right, is that the command normal, let's see if I have enough room to write all this, CDF, and then I go through and I have to define everything, right? My lower is 90, my upper is 100, my mean of y is 93.2, and my standard deviation of y is 3.6. So the normal CDF, with all those defined out for me, gives an area of 0.7835. The other way I could do that is with z-scores, right? I could go through and I could calculate the z-score of 90 and 100, right? 90 minus 93.2 divided by the standard deviation. I could also calculate my z-score for 100. And so after I have found the z-score for both 90 and 100, then I would have my probability. Here, let's change colors real quick so we realize that we're doing this a different way. Okay, and you can do this whichever way you prefer, right? So I could do then I'd have my probability. My first z-score is 89, and my negative 0.89, and my next one is my z-score for 100 is 1.89. So I'd be looking for that probability, okay, using my tables, my z-score tables, right? I get 0.9706 minus 0.1867, which gives me 0.7853. Again, very, very close to one another. So after this, I need to do step 3. And step 3 is to actually answer the question. Okay, and so in step 3, when I'm actually answering the question, this is when I put stuff in context and interpret what I'm doing, right? So I'm taking that information and I'm saying that there is about a 78% chance that the water temperature meets the recommendations on a randomly selected day. So there is about a 78% chance the water temp is safe on a randomly selected day. And that's how we would solve that problem. So now let's take a look at what's going to happen when we decide to combine random variables. So again, we're back to Pete Jeep Tours here. So on the top there, we've got his probability distribution for his number of passengers. His mean being 3.75 and his standard deviation being 1.089. And now we learn that his sister Erin lives in another part of the country, and she wants to basically copy Pete's business. So after a year of business, Erin discovers that the number of passengers Y on her on her half-day tours has this probability distribution down here of 2 passengers, 0.3, 3, 0.4. You'll notice she only can have 5 passengers in her vehicle. So Erin's mean, so the mean of y is 3.10 and the standard deviation is 0.943. The question here now says how many total passengers T will Erin and Pete have on their tours on a randomly selected day. So basically we want to know if we want to know what they both have. Okay, and the second part there says how many more or fewer passengers will Pete have than Erin on a randomly selected day. So to answer that, we need to look at x minus y. Okay, so when we're doing these, we can combine the two. The sum of the random variables, okay, so my sum of the random variables here, to find the mean of t, I can just add the mean of x plus the mean of y. Okay, and that would give me the mean of t. So in this case, it would be 3.75 plus 3.1 would give me a mean of 6.85 passengers per day. So again, that's looking at Pete and Erin together are averaging a mean of 6.85 passengers per day. So for any two random variables, x and y, if t equals x plus y, so if t equals x plus y, then my expected value of t, remember this is my expected value of t is going to be, I'm going to be able to add the two means. So now let's take a look at what this does to the variability between the amount of passengers, right? So Pete, who is x, right, he can have between 2 to 6 passengers, right? So that's what he can carry in his car. Erin, who is y, right, she can have between 2 and 5 passengers. So they have a different variability there, right? The Pete's range is 4, while Erin's range is 3. So my range of T is going to be my total number of passengers, okay, between 4 and 11. So for T, right, I'm going to have 4, because that's the minimum. They each have 2 passengers, right? And then I'm going to have 4 and 11, right? Because Pete can have 6 and Erin can have 5. So my range here is going to be equal to 7. Is going to be my range of T, which is the same as my range of T equals my range X, plus my range Y, right? Where my range X was 4 and my range Y there was 3, which gives me 7, which makes sense that I'm going to have more variability. I'm going to have this bigger spread when I'm combining both Pete and Erin versus when I'm just looking at Pete or just looking at Erin. If I want to calculate the probability of T, okay, so if I'm looking to calculate the probability of T, remember again that T is X plus Y. So if I'm looking to calculate the probability of T, I can only do that if X and Y are independent. If X and Y are not independent, then I cannot calculate the probability of T. Okay, so for independent random variables, knowing whether an event involving X alone has occurred tells us nothing about the occurrence involving Y alone and vice versa. So that's how we're going to know if they're independent. Okay? That I've got an event that involves X having nothing to do with an event that's involving Y. Okay? Remember, no association, we looked at a scatter plot. Most models for these are going to assume independence, especially when the outcome appears unrelated to one another. For instance, in this example, they're in two different, completely different areas across the country from one another. So the thought process would be that the people that are touring Pete's and the amount of passengers that Pete is taking each day is not going to impact the amount of passengers Erin is taking each day. It's not like they're in the same place competing with one another and taking, passengers away from each other. Okay, so let's look at this example a little bit further. So again, we've got t equaling x and y as before, but x and y are independent random variables. The probability of t equaling 4. So the probability of t equaling 4 can only occur one way, which is that they each both take 2 passengers. And so the probability of t equals 4 is the probability of x equals 2 and the probability of y equals 2. So when I multiply the probability of x equal to 2 times the probability of y equal to, okay, if going back to our previous probability distributions that we saw before, right? Pete's probability of having 2 passengers is 0.15. Erin's probability of having 2 passengers is 0.3. And so when I multiply those two probabilities together, I get 0.04. So my probability that t equals 4 is 0.045. Okay, and when I look at t equaling 5 passengers, there are 2 ways I can get that. Pete can have 3 passengers and Erin can have 2, or Pete can have 2 passengers and Erin can have 3. So I need to calculate both of those ways. Okay, so the probability of Pete having 2 and Erin having 3 plus the probability of Pete having 3 and Erin having 2. So 0.15 times 0.04 plus 0.25 times 0.3. Again, these probability distributions are coming from, we've seen them before, from the tables that we've seen before, okay, which would give us a probability of 0.135 that t equals 5, that they have a combined total of 5 passengers. And you would continue down the length of the table until you got to t equals 11, which can only be done one way, which would be Pete having 6 passengers and Erin having 5 passengers. If I look at my histogram, that histogram shape should look pretty familiar. Okay, so I'm not seeing any changes to shape because we don't see any changes to shape here. Okay, and so let's look at what this is going to do then to our mean. Okay, so once I've found my probability distribution, okay, if I want to determine the mean of t, well, the mean of t is going to be the mean of x plus the mean of y, which is was given to us earlier, 3.75 plus 3.1, which is going to give me 3.85, which means combined they have an average of 3.85 passengers on any randomly selected day. Okay, if I want to look at standard deviation, I cannot just combine the two standard deviations. So if I want to look at standard deviation, I need to calculate variance first. Okay, so I'm going to shrink these numbers down just a little bit, put it off to the side. Okay, so I need to calculate variance first. So when I'm doing my variance of t, okay, I can add the two variances together. Okay, so I can add those together, and from previous calculations, my variance is 1.875 plus 0.89. Remember, when I calculate variance, I am taking the data point minus the mean, squaring that value, and multiplying it by the probability that that will actually happen. And then I need to add all of those values together. So my variance here is 2.0775. Now I can find my standard deviation of t, where my standard deviation of t is going to be the square root of the variance of t, which is going to give me 1.441, which if you go back is not equal to adding the standard deviation of x plus the standard deviation of y. Okay, so we cannot add those two together. Okay, let's look at this example involving SAT scores. So I've got the college using SAT scores for admission. Experience has shown the distribution of SAT scores among its entire population of applicants is down below. Math score, mean of 519, critical reading score, mean of 507, standard deviation of the math score, 115, standard deviation of the critical reading score, 111. What are the mean and standard deviation of the total score? So total score being X plus Y for a randomly selected applicant. Well, if it's a randomly selected applicant, I can find my mean of my total score by adding the two scores together, combining the two variables together, meaning my mean total SAT score would be 1,026. Okay, I cannot do variance or standard deviation here though, because these two things are not, my math and reading score here are not independent of one another. Okay, so, and it would make sense that if they score higher in one, they probably score higher than most in the other one as well. Okay, and so these two are usually linked or not independent events, and therefore I cannot calculate variance and standard deviation for these. Okay, so let's go back to Pete and Erin again. Okay, I'm going to leave all the work and stuff here, and then we'll just kind of point things out and talk about it so we can move through this a little bit faster. So we've got X defined as the number of passengers Pete has, Y the number of passengers Erin has. Okay, just a reminder here that this is our mean and standard deviation of X and our mean and standard deviation of Y. Pete charges $150 per passenger. Erin charges $175. I want the mean and standard deviation of the total amount that Pete and Erin collect on a randomly chosen day. So we're going to assign W to be their total they're collected. Okay, the total money they collected is going to be how much money they collect times, or how much money they charge times the amount of passengers they have. So again, Pete charges $150, but Erin charges $175. If C is how much money Pete collects, right, 150 times X, and G is how much money Erin collects, 175 times Y. Okay, that makes W then the total that they both collected equals C plus G. So we can use what we've done before and see what happens when we multiply by a constant, right? So my mean of C becomes 150 times the mean of X. Okay, because I'm multiplying by that constant of $150. He always charges $150. Okay, and so Pete's mean collection here is $562.50. His standard deviation is, because standard deviation is affected by multiplying and dividing a constant, so his standard deviation here is 150 times the standard deviation of X. So his standard deviation is $163.46. And then we do the same down here for Erin. Erin charges $175 but has a mean of 310. So she gets an average collection of $542.50 with a standard deviation of $165.03. So now I can figure out what the mean of W is by adding these two means and getting a total here of $1,105, which tells me on average Pete and Erin are collecting a total of $1,105 together. Okay, these are independent random variables, so I can calculate variance, and then from there I can calculate standard deviation. Remember, I cannot add standard deviations. Okay, I have to calculate variance and then take the square root of the variance. So remember, when I'm calculating the variance here, I've got squares involved. So I've got the variance of C, okay, which is going to be 163.46 squared. So the standard deviation of C squared plus the standard deviation of G squared gives me $53,954.07. But when I want the standard deviation of that, I then need to take the square root of that total to give me my new standard deviation of $232.28, meaning that they're going to collect on average $1,105 per day with a standard deviation of $232.28. A quick point that we want to make is that x plus 1 plus x2 does not equal 2 times x. Let's go back to our roulette wheel for a second and we can see that. Okay, if I had let's look at two $1 bets versus a $2 bet, right? X1 plus, I can't write a plus sign, plus x2 is the same as two separate $1 bets, whereas 2x is the same as one $2 bet. Okay, well, remember my average was, my mean of x here, my average was losing 5 cents. Okay, so that would make, if this is y, that would make my mean of y, my expected would be a loss of 10 cents, okay, where my mean of t here would also be a loss of 10 cents. But when I calculate standard deviation for both of these, I get a deviation of $2 for my $2 bet, but a deviation of $1.41 for my two individual $1 bets. So my average is the same. I'm on average losing 10 cents for each one of these bets, but my $2 bet gives me that bigger chance of a quote-unquote big payout. Okay, one more example back at the car dealership here. So this time, in addition to cars sold during that first hour, we've got information on cars leased during that first hour. So step 1 here asks us to find and interpret the mean of t. Well, to do that, right, my mean of t is going to be my mean of my cars sold plus my mean of my cars leased, which is going to be 1.1 plus 0.7, which gives me a total of 1.8. So when I interpret that, that tells me that over many Fridays, I'm going to sell or lease 1.8 cars in that first hour that that they're doing business on average. Okay, number 2 asks me to find my standard deviation here of t. So when I'm finding my standard deviation of t, remember I have to find the variance of t first. Okay, so when I find the variance of t here, so variance of t, that is going to equal, right, my variance of x plus my variance of y. I do know the standard deviation of x, which is 0.943 squared. Okay, I know the standard deviation of y, which is 0.64. I need to square that for the variance. When I square those and add them, I'm going to get 1.2988. That's my variance. I still need to find the standard deviation, which means I need the square root of 1.2988, which is going to give me 1.14. Okay. Now, part 3 here says the dealership's manager receives a $500 bonus for each car sold and a $300 bonus for each car that is leased. Now I need the mean and standard deviation of the manager's total, right, that he calculates. So let's look at what this is going to be for, let's define that as B for both. Okay, so my mean here for both is going to be my mean of the cars that are sold times the constant times his bonus, plus the mean of the cars that are leased, again, times the bonus for that, which is 300. So when I sub my 1.1 times 500 plus 0.7 times 300, I get $760. So that is going to be his mean or his average bonus during that first hour that they are doing business on a randomly selected Friday. Okay, if I'm looking for the standard deviation of B here, okay, I'm going to need to, again, I need to calculate the variance. But remember, when I calculate variance, when I multiply variance by a constant, I have to square that constant. So let's come over here where I have more room to write all this. So if I'm going to calculate the variance of B, then I need to square the constant multiplied by the square of the standard deviation. Okay, and then I can add that again to the constant squared of y of leasing times the standard deviation of leasing squared, which is going to give me $259,176.25. But to get the standard deviation of B, I need the square root of that, which is going to be $509.09, telling me that he is going to have a standard deviation from that $760 average of $509.09. So what if I want to subtract random variables? So if I want to subtract random variables x and y, so the difference of x and y is going to be x minus y, okay, which is going to tell me then that my mean of the difference, or the expected difference, is going to be the mean of x minus the mean of y. Order is really important here. You have to put them in the correct order. Positive and minus, especially because you're talking about context here. So that's going to be important here. Okay, my variance here for D is going to be the variance of x plus the variance of y, which will then allow me to calculate the standard deviation. So even though I'm subtracting, I'm looking for the difference between these two random variables, I still am going to add the two variances together. Okay, let's look at another Pete and Erin example. Okay, so let's look at this problem here where we've got your reminders here of the amount of the mean of Pete's collections, as well as the standard deviation, as well as the mean of Erin's collections and her standard deviation. So our problem here is to calculate the mean and standard deviation of the difference between the two collections, okay, and the amounts that Pete and Erin collect, and interpret this in context. Okay, so if we're looking for the mean here, remember I can calculate my mean by just subtracting the two. Okay, so my mean difference here is $20 a day. So on average, and because it's a positive value, it's telling me that Pete on average collects $20 more than Erin does on some days. Some days more, some days less, but my average collection is $20. Okay. Because these are independent random variables, okay, I can calculate variance and I can calculate standard deviation. Remember, even though I am subtracting the two variables, my variance is still the sum of the two. So I am calculating my variance, so squaring my two standard deviations, adding them, and then getting the standard deviation value of 232.28. Okay, so that's going to be my standard deviation of the difference in the amounts collected by Pete and Erin. So my average difference is $20, but the difference on individual days will vary by about $232. Okay, so another example here. We're back at this car dealership, and we're looking for finding and interpreting the mean of D. So the difference between when cars are sold versus when cars are leased. So if I am interpreting the mean of D, I'm calculating the mean of D here, right? My mean of D is going to be equal to my mean of X minus my mean of Y, from my 1.1 minus 0.7, which gives me 0.4, which tells me that over many, many Fridays, the dealership sells about 0.4 more cars than it leases during the first hour of business. This is a very specific problem, and so you have to include all of that into your context. You have to include that this is only on Fridays, that this is only during the first hour of business, and that they're selling 0.4 more cars than they are leasing on average. Okay, when I'm looking to find the standard deviation for D, remember to find the standard deviation, even though I'm subtracting it, I need to find the variance, and to find the variance, I'm going to add the two. right? So my standard deviation is my square root, right, of the variance. So my variance of D, right, I have 0.943 squared plus 0.64 squared, which gives me 1.2998. When I take the square root of the variance of D, I get the standard deviation of D, which is 1.14. And then it tells me for part 3 here that the dealership's manager gives me the bonuses again. Find the mean and standard deviation of the difference in the manager's bonuses, bonus for cars sold and for cars that are leased. So if I'm looking here for the difference between the mean difference here, right, my mean difference is going to be 500 times 1.1, because that's the bonus for the average, and that's his average number of cars sold, minus 300 times 0.7, because again, that's the bonus for the lease and the average number of cars that are leased, which gives me $340, which tells me he gets an average bonus of $340 during the first hour of business on many Fridays, over the course of many Fridays. Okay, and then when I'm looking for standard deviation here, okay, again, I need to calculate the variance first. Okay, and I'm going to, since I'm multiplying by a constant, remember when we multiply by a constant, we have to square that constant. So when I'm looking for the variance of D here, I'm squaring 500 times 0.943 squared plus 300 squared times 0.64 squared, which gives me that humongous number again. And when I take the square root of that, I get 509.09, which tells me that he has a standard deviation from that average of $509.09. Okay, we're going to do 2 more examples of normal random variables, one sum of normal random variables, one difference of random variables, and then we'll be all set. Okay, I left some of the work up there so that you could see it a little bit, and we can move this a little bit faster. So what we have here is Mr. Starnes liking sugar in his hot tea. He needs between 8.5 and 9 grams of sugar for it to taste okay. While making his tea, he adds 4 randomly selected packets of sugar. The amount of sugar in these packets follows a normal distribution with means 2.17 grams and standard deviation of 0.08 grams. What is the probability that Mr. Starnes' tea tastes okay? So basically, I want to know the probability that he got between 8.5 grams in that cup of tea and 9 grams of sugar in that cup of tea. So remember, when we do these with normal problems, we have our 3-step process: stating the distribution and the values of interest, performing the calculations, and then actually answering the question. So for step 1 here, my distribution and values of interest. Okay, so I've got X being the amount of sugar in a randomly selected packet. Okay, so that would put X1 as packet 1, X2 as packet 2, X3 as packet 3, etc. Each of these random variables has a normal distribution. So I've got a mean of 2.17 grams, standard deviation of 0.08 grams. So I want the total amount of sugar in his tea. So I need to figure out what T is going to be equal to. So I'm going to add all of these together, and I'm going to get a mean value of 8.68 grams on this normal distribution. So when I draw my picture here, right, I've got, at my mean here, I have 8.68 grams there. Okay, so total grams of sugar. And what I'm looking for, right, is that I have between 8.5 and 9 grams of sugar. So I'm looking for this, and this curve is a normal curve, mean of 8.68 with a standard deviation of 0.16. So let's look where that came from, right? So when I want to calculate standard deviation here, remember I have to calculate variance first. So when I'm calculating variance here, I'm calculating it for each of my sugar packets. Okay, I had 4 sugar packets. They all had a standard deviation of 0.08, so I square all of those. I add them together. I take the square root of that and I get the standard deviation of 0.16. I have to have this when I draw my picture. I need to identify that normal curve, and that's how I identify that normal curve. So step 2 then is going to be that I actually perform these calculations. So when I go to perform these calculations here, again, I can do it on the calculator, or I can do it using z-scores. Okay, I'm going to show you z-scores this time. Okay, so if I'm using z-scores, right, I've got my first z-score, 8.5 minus 8.68 over 0.16. Gives me negative 1.13, and then I need to use my table on my formula chart to apply that information. And then z equals 9 minus 8.68 over the standard deviation of 0.16, which gives me a z-score of 2, which again I usually need to use my data table. And remember, my table tells me the area to the left of that score. Well, I want the probability that I am between negative 1.13 and 200. And so when I get this at numbers from my table, I get 0.9772 minus 0.1292, which is going to be equal to 0.8480. If I'm using technology, again, I can use that normal CDF, and then I need to define everything, right? I need to define the upper, the lower, the upper, which would be, the lower, which would be 8.5, the upper, which would be 9, my mean of 8.68, and my standard deviation of 0.16. And when I do it on my calculator, I should get about 0.8470. Okay? And then step 3 is going to be to actually answer this question. So the actual answer to the question now is going to be that there is about an 85% chance that his tea, tastes right. Okay, so let's look at what we have going on with this one. So with this one, I have a diameter C of a randomly selected large drink cup at a fast food restaurant. Normal distribution, mean of 3.96 inches, standard deviation of 0.01 inches. Diameter of the lid also follows the normal distribution, 3.98 inches, standard deviation of 0.02 inches. For a lid to fit on the cup, the value of the lid, so the diameter of the lid has to be bigger than the value of C, but not by more than 0.06 inches, because then it will be too big for the cup. So my problem here is, what's the probability that a randomly selected large lid will fit on a randomly chosen large drink cup? Again, we need to do our 3-step process. So let's look at step 1, stating the distribution and values of interest. So my random variable here, D, is going to be the lid minus the cup size. Okay? So the size of the lid minus the cup, and that's going to represent the difference between the diameter of the lid and the diameter of the cup. Okay, and so when I calculate the mean for this, I can just subtract the two means. Okay, and so my mean difference between the two is usually 0.02 inches. Okay, and when I calculate variance to then get standard deviation, I get a standard deviation of about 0.0224. So I want the probability that the difference is between 0 and 0.06 inches. Okay, so when I sketch this out, right, so when I sketch out my normal curve here, I've got my mean of the difference is 0.02. I want to know when I have probability between 0 and 0.06. Right, so 0.06. I want to know this area here. I need to define this curve. So it has a mean of 0.02 and it has a standard deviation of 0.0224. Okay, and so I've set up my parameters of interest, I've set up my values of interest, and I've talked about what my distribution was. So step 2 here is to actually perform my calculations here. So this time we'll do it on how you would look in the calculator. So when I am performing my calculations here, I'm going to write down, if I'm using my calculator, that the command normal CDF, and then I'm going to go through and define everything, right? With my lower at 0, my upper is at 0.06, my mean of the difference is at 0.02, and my standard deviation is at 0.0224. It gives an area of 0.7770. Okay, and so what that is going to tell me then is going to be step 3, which is going to be my actual answer, which is that there is a 78% chance that a randomly selected lid will fit on a randomly selected drink cup. In other words, about 22% of the time the lid will not fit the cup. Okay? All right, that is transforming and combining these normal random variables.